I'm Zihan Li, a PhD student in Tobias Professor's Pinkenberger's group. I'm mainly working on the design and fabrication of this nabe integrated photonics. So today I will give a simulation process for this nabe, this integrated photonic waveguide. The difference between the silicon nitride and this nabe is the cross-section structure. For silicon nitride, you can use a perfect rectangular as the waveguide, and it has a very straight sidewall, and you only have this rectangular as your core of the waveguide. But for the lithium nabe, due to the fabrication limits and also some performance trade-off, we have to use some cross-section like this. For these structures, we usually have a slope sidewall. It's not a 90 degree, it's usually a 60 to 70. So this slope sidewall will increase the mode value in the bottom area. And the second, the most important thing is for this nabe we usually have a slab layer. So when we etch this nabe materials, we don't etch through it. We leave a very thin slab layer at the bottom. And this thin slab layer will cause a lot of bending loss in the silicon nitride platform. As you can see here, when we use a 20 micrometer band ring resonators, the mode can leak to the slab layers. And in that case, when the slab layer becomes thicker, then the leakage becomes larger. Then you can increase your bending loss to almost dB, several dB per meter. So in that case, this bending loss has larger limits on the US minimum radius or the minimum band. To do the simulation, we usually use a geometry structure like this. It's a very simple. We have the silicon dioxide cladding and the buried silicon oxide, and also the lithium nabe layer. But one difference compared to the silicon nitride platform is in here. We cannot use a rectangular shape to make the waveguide. We have used this polygon to build this waveguide and also the slab layer. I think you can find my model and this presentation in the Google Drive. And here, I only use the PML layer in one side because when we simulate the bending loss, the mode will leak it to this direction. So we don't the absorption layer in other direction. Here I just list all the parameters that you may need for these simulations, or you may need to construct these structures. And here just show it. Yes.
Would there be a disadvantage to have CML on all sides?
No other one. I just because on one direction this PML is enough, so we don't need in other directions. Because PML is not such perfect, so it also can induce some fake mode or some unexpected reflection from that layer. I can show you this fake mode in the other slides. And here is some.
What did you always?
This one is come from the performance of this UO modulation. That's a longer story. For lithium nabe is electro-optical modulations. When we apply some external electrical field, it can change the reflective index of this material. But this material also has a very large dielectrical constant. If you etch through the lithium nabe and then put the electrodes on the side, then because in the center the dielectrical constant is very large, and in the cladding in the gap between the lithium nabe and your metal is air or silicon dioxide, the dielectrical constant is about 4 or 10 times smaller than lithium nabe. So you will get a very small electrical field in your core. So with this slab, it can enhance the electric field in the core and then increase the modulation efficiency. Because this part is not related to this simulation, I didn't include here. Yeah, this is the basic structure we need to simulate the bending loss with this slab. And also, I show you how to use this polygon to construct these structures. And here is a reflect index I choose. Another difference maybe in the future, because this Navi is also a good material to generate the solitons or the MicrocomSys. In the future, if you want to simulate this material for some practical experimental designs, you shouldn't use these single numbers because this Navi is a single crystal. It has an anisotropic reflex index in different directions. Here we just use this single number for the exercise. Then what will happen if we simulate the binding loss with the slab layer? Then we will get this two mode. When the unknown asks how to find the correct mode, like a core mode, someone proposed we can check the effective index. But actually for this slab mode, you see almost all the energy, all the mode area is confined in the slab layer. So this two mode has very similar effective index. So you cannot distinguish this two mode by this effective index. And in the practical, in the actual device, we only have this mode for the ring or for the waveguide. And this one, because we have a continuous slab layer, this mode will just leakage away, so we will lose this mode. Then how to simulate, how to distinguish these two modes? Here we use some better or some automatic method, not choose by ours. So the solution is at first we need to simulate enough modes. We need to make sure that in the solution we have our correct mode instead of all the fake mode, and then we can think about to calculate the energy ratio in the core, because the core mode it's almost confined all the modes in the core, but for the slab mode there most nothing in the core. So we can compare the ratio, the energy ratio between different modes to decide which one is the correct mode. Yeah, then we select the core mode. Then how to do it in the practice? At first, we need to define the core. For silicon nitride, you can just use your waveguide as the core area. But for the lithium Navi or for this slab waveguide, you need to use some different structure to create the area of the core waveguide. Here, I use the two line segments to confine the area of the core. And here we need to use this geometry structure named the line segment. And then the second one is to calculate the energy ratio. At first, we need to calculate the energy of this core, and then second, we calculate the energy, the total energy in the simulation area. To do this process, we can use this operator named the integration from the definition and the nonlinear couplings. I also include all these steps or these operators in my model, so we can do it later. Then the next one is just to calculate the ratio. Is for this step you don't need to be very rigorous in the physical or in the mathematics. We just need to know how much field we can confine in the course. So in here, I just integrated the normal E, the normal electrical field of the core or of the total areas. Because with this number, we already can distinguish the different modes. Then the second one, we just start simulation as unassigned. In here, we calculate 40 modes, and then in the list of this long list of simulation, you can find the effective index of each mode is actually very similar. So you don't know which one is a good one, which one is incorrect. Because except this slab mode looks like this, we also have some weird reflection and physical reflection from this PMLA layer, and it can give you a mode like this. So this one is probably reasonable, but this one is not reasonable for this.
Yeah, just to add, from the solution of the problem that you're facing, you guys have 6.2 version of COMSOL, and already say that it is 2D 8-axis symmetric. So I think COMSOL rectified their own mistake that they had in the model.
Yes,
you don't. Yeah. So like for example, me and Zihan both have refractive index multiplied by the radius. I also showed you the same. Just remove the radius. Just put refractive index. 1.5 for a second. He's saying 2. Put that.
Yeah. I corrected it in my model, but not in.
Yeah, but I learned it right now. So just remove the radius, just put the refractive index and the whole simulation model will run.
Then next one. Yes.
To go back one slide. Now we are looking for this modes with a smaller real part, the refractive index.
Oh, you mean here?
Yeah.
Yeah. This is just some general setting.
Okay.
Either Zheru or Jinying explain why do we choose this value. Because for the mode, when we search the mode around some values for this value, we usually use the reflective index of the material as the starting point. And the mode, we know the mode is not fully confined in these core materials. So the effective index is slightly smaller than your material in your materials reflective index. So that's why we choose to search the smaller real part, because we know the mode has smaller effective index than the material. It's not necessary, but it's just more convenient. Then from the simulation results, we can compare this the ratio of this field ratio and choose the largest one, this one, and then we can get the correct mode in these simulations. Basically, this 5 steps is how to show you how to find the correct mode with this fake modes. And as the exercise, I created a model and also some MATLAB script in the Google Drive. Maybe you can just try to simulate this binding loss for different FSL radimeters. And here is the parameter I used in my model. And for the answer, because I also cannot find the lessons for this for my simulation, so I only get the result for the half-edged is not will get. This one is more difficult, and if you simulate this fully edged one, as you proposed, you can find the loss can be significantly lower than this is half-edged one. So, then we start the exercise.
Yeah, so we can just go back to the exercise for you, just to show quickly. I think if you guys can maybe wait for 15 minutes till 5:30, will be fine.
Yeah, so the thing that we've seen earlier, we dedicated like about an hour at the end of the day.
Yeah.
So what it is for is like now we're doing some half exercise and half done. So of course at 5:30 you're free to go, but for those of you that want to stay in the exercise, they're around 12. So you know you can step out and come back.
So if you guys
can open the previous model,
remove the multiplication R SIN 1 meter, just remove that and just only put 1.54 and run it. Do you see? Now you can
you see the
largest
refractive index of each
radii, and that is confined in the waveguide? Okay. Now if you can go to the derived table, can you go to the result?
I'll share first.
Can you stop sharing? Okay. Is it close, right? Your model is close, right? But then you can also see. So all of you guys can see the derived result. You see that if you select the parameter as radius all, sorry. Radius all is empty. Yeah, you have to compute. So I'll just. So you have to press. So if you go to results, after running, go to derived values. So you must have not anything in the derived value, right? So now right click, do it with me. Right click and go to global evaluation. Right click, do this global evaluation. And now under global evaluation, if you click, so you will get something like this. And now there, just enter this formula. You can copy paste on the slide. Enter this formula just as the first row. Forget this core by total. Just enter this formula. That formula must be in the slide. You can copy paste actually. Have you done it? You're running it? This expression is in the slide. You can copy this expression. Yeah, it's empty. You have to add it. So you go and click Does it work for anyone? Work? Good. So can you generate this table now? So select this parameter selection all, affecting index last. So study one is not there. You ran the model, right? You ran, right? You did it. So can you first select? Can you do this first? Then these are two not appearing. These two. This you have to enter manually. So what's missing? So select radius, select all, and then select last. So select all and then select last. I'll mention. But first, at least generate without this column. Generate this, but don't compare with these values. These values are for the exercise. It should be slightly different because you are doing for 200 nanometer thin silicon nitride. This is 100 nanometer. You must have something, but not some weird values. Some like positive numbers, like decimal numbers. Okay. Did you get it? You have these like three values here.
I have 1.3.
Yeah, it's acceptable. And what is the minimum radius? What is the value? No, actually. The last activity is now.
This is probably the wrong expression.
Because now the expression also has RSA. Yeah,
Because then we get directly
yeah, that's correct. So I think you have to use the RSA. Radius, I'm dividing the radius again. You have to use this. Yeah, is it right? No, yeah. So here, so you have to multiply by one. Yeah. Okay, so since so you have got so now you have got the result. So you can export. There is a go to click this arrow and just save this file. Click this arrow once you have got it. Because you got the right value. The highest value should be around 4 point something, right? That's correct. So you just click this arrow and then save it. Save it in the same folder where your MATLAB file is. Save it in the same folder. Whatever you want to save as. Done? So you have already saved it? Yeah, so look, can you open the MATLAB file? And in the file name, just change the file name to your file name, whatever you have saved as. Just save it, put it there. I think you also got it, right? So can you now do this? So you can actually can you click on this button here and export? Can you click on this button and save the text file? This will export the table into a text file. And then you can go to the MATLAB file, which is there. And instead of the file name, just change the file name of the save which you have saved. Just put it here. Just change the file name and run it. The error is still there. I think we can run it again. It runs, right? It runs. It works, right? Good. Okay. So if it works for one, it should work for everyone. Yeah. So can you run the MATLAB file? And does it work for you? This works? So your highest bending loss is around 4 point something, right? Yeah. Now the exercise was actually to make the waveguide 100 nanometer and 2.8 micron wide and run the same thing again. To have to actually then to plot this graph actually. Yeah. 2.8 micron wide and 100 nanometer thin. So you can change the parameter, you can change the thickness to 100 nanometer, is 200 right now, and change the waveguide width from 1.5 to 2.8. And you can run it again, find the bending loss from the table, export the table, and then run the MATLAB file. Yes. Yeah, so it works. Well, works for you? What was the problem? Okay. Yeah. Maybe, yes. So the radius, so for now, because you are much thinner, so the parameter of radius you can change. You can change the parameter of radius to be around. Wait, I will show you. So so instead of 75, 150, and 200, just go to 150, 250, and 350. You just have to find 3 points, and you can then plot the whole range. Just because now it is thinner, you would want to make a bigger ring. So just change this in your parameter for 100 nanometer thin. Yeah. Yeah, this one.
Sorry.
Yes.
In the parameters you set the width.
Width of the silicon nitride 2.8, height of the silicon nitride 100 nanometer, and then you go to the study parameter sweep. Okay. Go 150, 250, and 350. Something like that. Yeah. So I just did you change the radius? Like the parameter sweep? Can you go to parameter sweep? Yeah, did you change this one? 150, 250, 350.
Yeah, but then you can change the parameters. The parameters.
The parameter is same, it's fine, because this is sweeping anyway, so it will override what is written there.
Okay.
So this will override only this one, but the width and the height needs to be changed. Okay, so now you can run it. It's running?
Yeah.
Yes. Yeah. Okay, so you might see that Wait. Can you go to more analysis? So one more thing. For 100 nanometer, just listen one more point of attention here. Change this to 1.49 now because you are now even weakly confined. Now you are more of oxide you are seeing, very less of nitride. So even 40 modes are less. So maybe you simulate either 120 modes or change the refractive index and simulate 40 modes. So it's better, change it to 1.49 and then run. It will take a minute, it will just take a minute. Maybe 2 minutes.
What happened? I'm just trying to talk to you. The mesh. The mesh and also the. Where is it? I think we need to increase the PML.
Increase the PML.
Right, 1.55 divided by 1.5. But C is kind of more like logic. Yeah, but yes, I just wanted to improve the mesh because it was like super narrow. Okay.
Why did you choose
1.49? Because now the waveguide is even thinner. So you have more mode, like basically your mode is all C oxide, not silicon. Silicon 100 nanometer. You have like everywhere is oxide. So oxide refractive index is 1.5. So you would want it to be near 1.5. Either you keep 1.54 or whatever, keep simulating 100 more, 200 more, till you find that guide. Or bring your mode index near the thing and then find 40 minutes. Either you have to simulate a lot, keeping the refractive index constant there, or change the refractive index. And simulate less number. Because your effective mode index is basically what you see in the material. So if you have a very thin core and your mode is basically everywhere is around oxide, so it is near oxide, so it is near 1.1. If it is more inside nitride, it is moving towards 2. Nitride it is moving towards 2. So if you are very thick, like gamma C, like for frequency 4, you make thick waveguide. So the whole mode is inside. Their refractive index is 1.9. Yeah, but then, and maybe 40 modes are not enough. Maybe it will keep finding, but it might not there. Maybe then you have to put it to So I know beforehand what I did. So I know that 1.49 I need 40 modes. Otherwise you can keep that. So could you run it? Like, good. And then now let's plot. Now let's plot both 100 nanometer and 200 nanometer, what we just both computed in one plot. So that we have both two lines, so that we can replicate what we saw in the SI of the manuscript. So something like something. So now if you have, so you can just, you know how to operate with MATLAB, right? Just hold on to that figure and plot again on the same figure. You should see something like two lines like this. Like this. So my objective is to get something like this. So 200 nanometer. These two lines, if you are getting these two lines, the job is done. Remember to that the radius should not be entered in 6.2 COMSOL model. Even in the formula, the radius should be deleted. Like mode index, also while simulating, and also in the formula, it should be deleted. I mean this particular value. So there is no this term now. This term is not there. I just want everyone's attention here. This term is not there in the 6.2 latest COMSOL model. You need not divide by radius of the waveguide. The COMSOL has rectified its error, like actually. Yeah. No, but no, this was we did 2. We did 100 and 200. No, this particular 2 lines are the thickness of silicon nitride, not the area. This is the plot. This is the thick. This is the radius. You can see area, you can plot all the area. It is like a uniform line. Yeah, we have 2 lines. That I have plotted the log. The objective was because I want to replicate this and log lets you see like expand the lower frequency and lower variation. You want what is this?
No, because
There's an excitement by Zihan, but I don't know, like.
I would actually also like to
Another way to find out. But we can have this tomorrow. Simone, there's some doubt in the previous exercise from there. But we can discuss tomorrow then. We can call him tomorrow.
Yeah, I did not.
But why we can discuss tomorrow?
Yeah, because
So I'll also show you that there is slight variation and why that is. So
It could be for multiple reasons.
Okay, so this one. So you see these 2 plots? Is it near around the red 100 nanometer should be around 1000, 10 to the power 3. Correct? You can see it's not exactly like this. It's slightly shifted. Probably because of the different refractive indices that we are using. We are using a Selmayr equation or our own. They are using their own. That could be the difference. And this one, the blue one is 250 anyway. Our is 200. So obviously it's slightly different. But it should be near 100. And that should be near 1000. Is correct? Okay. In COMSOL, you want to plot like this in COMSOL? I think you can do that also. Without MATLAB also, but I think the plot quality is better in MATLAB or Python. Yeah, I think you can do that. You can do that. I think you can. I think there is a way you can import data and then plot it. You can do that. Table, yeah. Good. So almost everyone could follow it and could get this result, right? Great. Okay, then I conclude my session. And if there is anyone's doubt with Zihan's exercise, you can ask Zihan. Thank you.